We can think of a vector as an arrow. It has two key properties: magnitude, which is the length of the vector, and direction, which is where the arrow points. In contrast, a scalar is just a number. It has magnitude but no direction. For example, when you see a speed of 60 kilometers per hour on a dashboard, that is scalar. It tells you how fast, but not in which direction. But if you say moving east at 60 kilometers per hour, now you have a vector, because it has both magnitude and direction. Vectors are everywhere. Wind, ocean currents, gravitational fields, magnetic fields, even colors can be represented as vectors. The RGB, red, green, blue color model is a vector system. Every color is created by mixing red, green, and blue lights in different amounts. For example, pure red can be represented by a row vector 1, 0, 0, or by a column vector. Simply put, row vectors have their elements arranged in a row, while column vectors have their elements arranged in a column. Pure green is 0, 1, 0, and pure blue is 0, 0, 1. If there's no light at all, we see black, which corresponds to 0 vector 0, 0, 0. A 0 vector is a vector in which all elements are 0, meaning it has no magnitude and no direction. Now, an important detail: RGB color mixing is based on light, not paint. When you mix red and green lights, you get yellow, which corresponds to a vector 1, 1, 0. Red and blue mix to create magenta, which is 1, 0, 1. Blue and green mix to create cyan. This vector is 0, 1, 1. And when all three colors are at full intensity, we get white, represented by a vector of 1, 1, 1. We call this vector as all ones column vector, since every element is 1 and it is a column vector. This entire RGB mixing process is, at its core, vector addition, a topic we'll explore very soon. Vectors can be thought of as special types of matrices. A matrix is just a rectangular array of numbers arranged in rows and columns. Each element is uniquely identified by its row and column indices. A row vector can be seen as a matrix with one row and multiple columns, and a column vector can be seen as a matrix with multiple rows but one column. The coordinate system connects geometry and algebra, making vectors tangible and visible. Before introducing the Cartesian coordinate system, let's first consider a simple mathematical concept: the number line. A number line has three key elements: an origin, a positive direction, and a unit length. A number line is an infinitely extending straight line. On a number line, each point corresponds to a real number. If we position two number lines perpendicular to each other so that they share a common origin, we then create a two-dimensional Cartesian coordinate system. In this two-dimensional coordinate plane, every point can be written in the form x1, x2. x1 represents the horizontal position, while x2 represents the vertical position. A two-dimensional column vector x1, x2 can be seen as an arrow with its tail at the origin 0, 0 and its head at x1, x2. Still using RGB color model as an example, we can represent the horizontal and vertical directions with red and green respectively. Together, they construct a red-green plane. When dealing with a small number of vectors, or when we care about the locations of their heads and tails, we typically represent vectors using arrows. However, when there are many vectors, we can use scalar points to represent vectors directly. In this case, it's assumed that all vectors originate from the origin, and the scalar points indicate their endpoints. In this red-green plane, two special vectors are worth noting. The first one, is a unit vector, 1, 0, in the pure red direction. We call it E1. Please note that a unit vector has a length of 1. The other unit vector, 0, 1, is in the pure green direction. We call it E2. Any vector in this plane, such as x1, x2, can be decomposed into x1 times E1 plus x2 times E2. In other words, these two unit vectors, E1 and E2, serve as the framework that creates all vectors in the plane. This ability is called span. If we add a new number line at the origin, making it perpendicular to the existing two axes, we then get a three-dimensional Cartesian coordinate system. A two-dimensional coordinate system is like a canvas painted with red and green. The addition of the third dimension brings in blue, allowing us to perceive the full spectrum of the RGB colors. Thanks to rectangular coordinate systems, understanding vector addition becomes very easy. For two vectors A and B of the same dimension, vector addition means adding their corresponding components element-wise to generate a new vector. In the previous video, we mentioned that the RGB color model, adding red vector E1 and green vector E2 results in the yellow vector. And adding the red vector E1 and the blue vector E3 give us the magenta vector. Similarly, adding the green vector E2 and the blue vector E3 produces the cyan vector. And when we're adding all three vectors, E1, E2, and E3, we get the white vector. Now, how do we visualize vector addition? One way is to use parallelogram rule. When adding vectors A and B, we align their starting points. Then, treating A and B as adjacent sides of a parallelogram, the diagonal from their common starting point to the opposite vertex represents the vector sum A plus B. With this rule, we can construct a parallelogram where the red vector E1 and the green vector E2 form two adjacent sides. Then, align their starting points. Complete a parallelogram by drawing the other two sides. The diagonal from the shared starting point to the opposite vertex gives us the sum of E1 and E2, which is the yellow vector. Similarly, we can apply the parallelogram rule to find the magenta and the cyan vectors. Another approach to visualize vector addition is the triangle rule. For vectors A plus B, the triangle rule states that we place the second vector B so that its starting point aligns with the endpoint of first vector A. The resulting directed segment from the starting point of vector A to the endpoint of vector B represents their sum. Applying triangle rule to our RGB example, we can move the starting point of green vector E2 to the endpoint of red vector E1. The vector from the tail of E1 to the head of E2 gives us the yellow vector. Alternatively, we could shift the red vector E1 so that its starting point aligns with the endpoint of the green vector E2. Then the resulting sum is still the same yellow vector. This demonstrates the commutative property of vector addition, i.e., adding E1 and E2 is the same as adding E2 and E1. Now let's extend this to three vectors. In the RGB color space, if we apply the triangle rule successively to red vector E1, the green vector E2, and the blue vector E3, the final vector points to white, meaning E1 plus E2 and E3 give us white vector. There are two different ways to compute this vector sum. One way is to first compute E1 and E2, which gave us the yellow vector. Then adding the blue vector E3 leads to the white vector. The second way is to compute, firstly, E2 plus E3, which gave us the cyan vector. Then adding the red vector E1 also gave us the white vector. This demonstrates the associative property of vector addition. E1 plus E2 grouped together first plus E3 is the same as E1 plus the sum of E2 and E3. Scalar multiplication of a vector means multiplying each component of the vector by the same scalar to produce a new vector. From a geometric perspective, scalar multiplication of vector is a scaling transformation. Positive scalar stretches or shrinks the vector in the same direction, while a negative scalar does the same but reverses its direction. Multiplying a vector by 0 results in a zero vector. In the RGB color space, the red, green, and blue vectors can each be scaled by a scalar k. When k is in between 0 and 1, the vector's length decreases as k approaches 0, making the color darker. However, the direction of the vector remains unchanged, meaning the hue stays the same. In RGB color space, the all ones vector 1, 1, 1 represents white. Multiplying it by a scalar k produces a new color, gray. When k is close to 0, it shifts towards black. When k is close to 1, the color appears nearly white. By taking any color vector in RGB space and scaling it with values varying linearly between 0 and 1, we can create smooth gradient effects, adjusting the brightness while keeping the hue consistent. In vector operations, combining scalar multiplication with vector addition enables us to spine higher dimensional spaces. For example, given two non-zero vectors A and B, their weighted sum is called a linear combination. Simply put, a linear combination means creating a new vector by adding up multiple vectors, each multiplied by a scalar weight. If two non-zero vectors A and B are not collinear, we call them linearly independent. When k and t take all possible real values, the linear combination of two non-collinear 2D vectors can span an entire 2D plane. Similarly, in a 3D space, two non-collinear vectors can only span a 2D plane, but not the full 3D space. On the other hand, if two non-zero vectors A and B are linearly dependent, their linear combination remains on the same line. In the RGB color space, mixing red and green in different proportions forms the red-green plane. Likewise, mixing red and blue gives us the red and blue plane, while mixing green and blue creates the green-blue plane. Using all possible weights, the weighted sum of red, green, and blue together forms the full RGB color space. However, it is important to know that RGB color values are restricted between 0 and 1. They cannot take arbitrary values like real numbers. Therefore, strictly speaking, the space spanned by red, green, and blue is not a real vector space. Vector normalization scales a non-zero vector to have a length of 1 while preserving its original direction. For example, given a two-dimensional column vector 3, 4, its unit vector is 3 over 5, 4 over 5. We observe that after normalization, the vector's length becomes 1, but its direction remains unchanged. For this reason, unit vectors are also called direction vectors. The zero vector is usually considered to have no direction, but sometimes it is said to point in all directions. Moreover, when a non-zero two-dimensional vector is normalized, if its initial point is at the origin, its terminal point lies exactly on the unit circle. Clearly, the vectors E1, 1, 0, and E2, 0, 1 are also unit vectors, representing the directions of positive x1 axis and positive x2 axis, respectively. Their terminal points both lie on the unit circle as well. If a vector has a length less than 1, its terminal point lies inside the unit circle. If its length is greater than 1, its terminal point is outside the unit circle. All vectors originating from the origin and having the same length will have their terminal points on the circumference of a circle with that length as its radius. That means if we increase the length of a vector gradually, its terminal point moves along different circles of varying radii, forming a set of concentric circles. This leads us to the topic of vector norms we'll discuss very soon. In a plane, any non-zero vector A can be expressed as the product of its length and a direction vector. For example, vector A, 3, 4, can be written as 5 times its unit vector, 3 over 5, 4 over 5, where 5 is the length of vector A. Furthermore, a non-zero vector in the plane can also be written in the form 5 times unit vector cosine alpha, sine alpha. Alpha is the angle between vector A and the positive horizontal direction. This naturally introduces the concept of polar coordinates. Simply put, polar coordinates define a point's position in a plane using a coordinate system centered at the origin, the pole, and aligned with the positive x1 axis, polar axis. The polar coordinate system specifies a given point in a plane by using its radius r and angle theta. Cartesian coordinates and polar coordinates can be converted back and forth. In polar coordinates, the vector corresponding to r theta is r times a direction vector of cosine theta, sine theta. Apparently, its unit vector is cosine theta, sine theta. In three-dimensional Cartesian space, it is easy to determine the direction vector of any non-zero three-dimensional vector. For example, the direction vector of the three-dimensional column vector 2, 3, 6 is 2 over 7, 3 over 7, and 6 over 7. Similarly, the vector 2, 3, 6 can be expressed in the form length times direction vector as well. If the initial point of a three-dimensional unit vector is at the origin, its terminal point lies on the unit sphere. This naturally leads to spherical coordinates. For more details, please refer to the PDF manuscripts and tutor notebooks in the GitHub. Given two column vectors A and B of the same dimension, their inner product is obtained by multiplying corresponding components and summing the results. The outcome is a scalar. The definition for inner product of vectors appears quite simple, yet it contains profound geometric insights. From a geometric perspective, the inner product of vectors A and B is equal to the product of their magnitudes, multiplied by the cosine of the angle theta between them. The magnitude of vector A multiplied by the cosine theta represents the projection of A in the direction of B. We refer to this projection length as the scalar projection. Similarly, the magnitude of vector B multiplied by the cosine of theta is the scalar projection of B in the direction of A. For two non-zero vectors A and B, their inner product varies as the angle theta changes. Let's assume that the magnitudes of A and B are fixed. When the angle between A and B is 0 degree, the two vectors point in the same direction, also known as being parallel. In this case, the inner product is maximized. When the angle theta is an acute angle, meaning theta is greater than 0 degree but less than 90 degrees, their inner product is positive. When the angle is a right angle, meaning theta equals 90 degrees, their inner product is 0. At this point, we say that vectors A and B are orthogonal vectors. When the angle is obtuse, meaning theta is greater than 90 degrees but less than 180 degrees, the inner product of A and B is negative. When the angle theta is exactly 180 degrees, the two vectors point in opposite directions, and their inner product is minimized. Now let's explore relationships between different color vectors in the RGB color space. For red vector e1, green vector e2, and the blue vector e3, it is very easy to calculate that the inner product is 0 for any pair of them. This means that red vector e1, green vector e2, and blue vector e3 are mutually orthogonal, meaning their pairwise angles are all 90 degrees. In other words, e1, e2, e3 form an orthogonal set of vectors. Every vector in the blue-green plane can be written as the linear combination of blue vector and the green vector. This tells us that the red vector is perpendicular or orthogonal to the entire blue-green plane. Similarly, the blue vector is perpendicular to the entire red-green plane, and the green vector is perpendicular to the entire red-blue plane. Through very simple calculations, we can see that the angle between the red vector and yellow vector is 45 degrees. This means that although the two colors are different, the yellow vector contains some amount of the red vector, indicating that the two colors overlap to some extent. In RGB color space, there are many other pairs of vectors with 45-degree angle. Try to find them yourself. Additionally, the angle between the yellow vector and the cyan vector is 60 degrees. I encourage you to compute this result by yourself. The closer the angle is to 0 degree, the more similar the two color vectors are, meaning the color vectors are more alike and their overlap is higher. The closer the angle is to 90 degrees, the more different the two color vectors are, meaning the colors are more distinct and their overlap is lower. The result of a scalar projection is a scalar and does not contain direction, as the name suggests. The previous video mentioned that scalar projection is essentially a coordinate. For example, the scalar projection of vector A onto a non-zero vector B is the coordinate of A's orthogonal projection onto B. Conversely, the scalar projection of vector B onto a non-zero vector A is the coordinate of B's orthogonal projection onto A. Imagine a beam of yellow light passing through a red filter. Only the intensity of red component is preserved. This intensity value can be compared to the scalar projection of the vector yellow onto the vector of red. The yellow light vector is 1, 1, 0, and the red light vector is 1, 0, 0. The scalar projection of yellow light onto the red light vector is 1. Conversely, the scalar projection of red light onto the yellow light is square root of 2 over 2. We know that the length of yellow vector is square root of 2, and the red light accounts for half of it. Now let's look at vector projection. Vector projection is the product of coordinate times direction vector. This direction vector is the unit vector in the projection direction. For example, the vector projection of A onto B is the scalar projection of A onto B multiplied by B's direction vector. On the other hand, the vector projection of B onto A is the scalar projection of B onto A multiplied by A's direction vector. The vector projection of yellow light onto the red light vector is simply the red light vector 1, 0, 0. Now, think about this. What is the vector projection of red light onto the direction of the yellow light? When the yellow vector is orthogonally projected onto the red vector, there is still some left over. This remaining part is the green vector. The remaining green vector is perpendicular to the red vector. Simply put, green vector is the part of the yellow vector that the red vector just can't account for. In vector projection, this green vector also has a name. It is called orthogonal complement, also known as orthogonal remainder. In the diagram, the pink vector is the orthogonal complement of A in the direction of B. Clearly, this orthogonal complement is perpendicular to vector B. This diagram also shows that vector A can be decomposed into two components. One component parallel to B, the other perpendicular to B. We call this the orthogonal decomposition of a vector. The white light vector can be orthogonally decomposed into yellow light, blue light. Clearly, blue light is perpendicular to yellow light. Similarly, a white light vector can also be orthogonally decomposed into magenta light and green light. In RGB space, we can find nearly infinite decompositions of white light. Vector decomposition can be understood as the inverse operation of vector addition. It splits the vector into two or more components such that their sum equals the original vector. On the number line, it is very easy to see 5 is greater than 4. Even when the signs are different, like comparing -5 and 4, we can use absolute values to compare their magnitudes. The absolute value is just the distance between any number to the origin. But in 2 or higher dimensions, you cannot directly compare two vectors. Take two vectors like A 3 minus 4 and B 0, 5. Which one is bigger? To make this comparison possible, we introduce something called a vector norm. Simply put, a vector norm gives us a way to measure how big a vector is. A vector norm maps a vector to a scalar based on a specific rule. Then we can use the scalars to measure how big vectors are. Let's start with L1 norm. The L1 norm adds up the absolute values of a vector's components. For example, the L1 norm of vector A is absolute value of 3 plus the absolute value of -4, which equals 7. And for vector B, its L1 norm is the absolute value of 0 plus the absolute value of 5, which gives us 5. So according to the L1 norm, vector A is larger. So for a 2D vector x, the L1 norm's contours in the plane are tilted squares. A contour is a curve or shape consisting of all points which are at the same distance from the origin under a given measure. The L2 norm comes from Pythagorean theorem. Square each component, add them up, then take the square root. It gives us the straight line distance from the tail to the vector's head. For vector A, square 3, you get 9, square -4, you get 16, add them up, that is 25. Then take the square root of 25, which gives you 5. That is the L2 norm of vector A. Very easy for vector B, its L2 norm is also 5. So by the L2 norm, vectors A and B are equal in size. The L2 norm's contour lines in the plane are perfect circles. The L infinity norm is also called the Chebyshev norm, takes the largest absolute value among a vector's components. For vector A, take the absolute values, 3, 4, then pick the larger one, which means vector A's L infinity norm is 4. For vector B, its L infinity norm is 5. So under the L infinity norm, vector B is larger. And the contour lines of the L infinity norm in the plane are squares. To generalize these different norms, we define LP norm. As we can see for 2D vector x, as p increases from 1, its LP norm contour changes smoothly in shape. Now let's head into RGB space and look at norms of color vectors. In RGB space, vectors with L1 norm equal to 1 all end on a plane. With L2 norm equal to 1, the vectors and points lie on the surface of a unit sphere. With L infinity norm equal to 1, vectors' terminal points land on the 3 brightest faces of the RGB unit cube. You can use LP norm to measure the distance between any 2 points on a plane. But how do we store all these distant values? You're probably already thinking, a matrix. Matrices and operations on them, that's exactly what we'll dive into in the next chapter. See you then.